could an observer define left and right using only a fundamental experiment?
For decades, the physics community would have answered that question with just an absolute no.
Right.
Physicists treated mirror symmetry, which is known formally as parity, as this universal, totally unbreakable law of nature.
Like a foundational assumption.
Exactly. The assumption was that if you set up any experiment, its exact mirror image would follow the exact same physical rules.
Yeah.
It was just considered this elegant, self-evident truth.
Yeah.
But as we're going to explore today, the weak interaction ultimately revealed a pretty shocking reality. Nature actually distinguishes handedness in specific subatomic processes.
Wow. Okay, let's unpack this. Because our mission in this deep dive is to explore an independent Cosmora HQ overview of Chen Ning Yang's Nobel lecture.
Right, the law of parity conservation and other symmetry laws of physics.
Exactly. And we're going to basically trace the precise history of parity violation, because if you're listening to this, you probably rely on symmetries, at least intuitively, to just make sense of the physical world.
You expect balance.
Yeah, you expect balance.
Yeah.
So to understand how the universe actually tells left from right, we kind of have to look at this one specific theoretical mystery that forced physicists to, check their absolute blind spots.
The theta-tau puzzle.
Right, that huge crisis. So we'll move from basic symmetry and mirror reflection to the theta-tau puzzle, and then into Li and Yang's brilliant evidential audit.
Which is such a great piece of scientific history.
It really is. And that, of course, forced this freezing cold, highly complex cobalt-60 experiment that just fundamentally shattered our understanding of physics.
Completely rewrote the books.
Yeah. And from there, we'll look at the reality of parity violation, the nuances of helicity and chirality, the V-A weak interaction, and finally some modern symmetry tests.
It's a really profound sequence of events, mainly because, well, before we can break a rule of symmetry, we have to define the rule with actual mathematical precision.
Right.
In physics, a symmetry is essentially a rigorous scientific question.
Okay.
It asks whether a transformed experimental setup obeys the same dynamic laws and gives you the exact same probabilities as the original setup.
Okay, so let's try to ground this for the listener with a thought experiment.
Sure.
Imagine you're observing a physics experiment, but you are watching it through a mirror.
Okay.
The traditional sort of common sense expectation is that whatever physical process happens in the mirror has to be perfectly possible in the real world.
Right.
Like if a billiard ball bounces off a cushion at a certain angle, the mirror reflection of that bounce doesn't, violate any laws of motion.
Exactly. But to test this at the subatomic level, we can't really rely on the intuition of a bathroom mirror.
Right. Yeah.
We must define parity strictly as spatial inversion. So imagine a three-dimensional coordinate system.
Like an XYZ grid.
Yeah, an X, Y, and Z grid. The parity transformation takes every coordinate in space and flips them. So X becomes negative X, Y becomes negative Y, and Z becomes negative Z.
Oh, I see.
Intuitively, this mathematical operation is equivalent to taking a mirror reflection and combining it with a 180-degree rotation.
Okay.
It's a very precise, completely testable mathematical transformation.
Well, I want to push on how different physical properties behave under that specific transformation, because it feels like this is where the math kind of traps our intuition.
It does.
If I observe an object moving linearly, like let's say an electron shooting out of a nucleus, its momentum is a vector.
Right.
If we invert the coordinates, the direction of that momentum just simply flips. Forward becomes backward.
Yeah, you are describing a polar vector there.
Yeah.
Under the mathematical operation of spatial inversion, a polar vector just reverses its sign.
Okay.
But physical systems possess other properties, and this distinction is the theoretical crux of the entire discovery.
Oh, wow. Okay.
So consider spin or angular momentum.
Right. So if I picture a spinning top, like rotating clockwise, and I apply spatial inversion, so I'm flipping all the coordinates, the position of the top flips, but the rotation itself doesn't just reverse in the same linear way.
Precisely. Spin is an axial vector. Sometimes it's called a pseudovector.
A pseudovector, okay.
Yeah. The mathematical description of angular momentum is actually derived from a cross product of two polar vectors.
Oh.
Position and momentum. So because both of those polar vectors reverse their signs under spatial inversion, the two negatives cancel out.
Oh, right. Negative times negative.
Exactly. So the axial vector does not reverse its sign. It transforms entirely differently than ordinary momentum under parity.
So we have two types of vectors behaving completely differently under spatial inversion.
Right.
If I'm trying to build an experiment to test if nature respects the mirror, this seems like the perfect theoretical wedge. You just look at the relationship between something spinning and something moving.
It is the perfect wedge. That's exactly it. Because momentum and spin transform differently. Looking at the correlation between nuclear spin, which is an axial vector, and emitted electron momentum, which is a polar vector,
Right.
that gives you a perfectly orientation-sensitive test for parity.
Okay, I think I'm following.
If you align the spin of a radioactive nucleus and you watch the direction it emits a particle, you can mathematically compare that emission to its spatially inverted counterpart.
So if parity is an unbroken law, the emitted particles must shoot out equally in both directions relative to that axis of spin.
Yes, exactly.
Because if the atom preferred to shoot electrons at the North Pole rather than the South Pole, its spatial inversion would show the opposite preference.
Right.
And if the mirror universe behaves differently than the real universe, then parity is broken.
You've got it.
But if the test is theoretically that straightforward, why did it remain this massive blind spot for so long?
Well, it really came down to the sheer power of extrapolation.
Okay, how so?
Parity conservation had incredibly strong, verified experimental support in electromagnetic interactions and strong nuclear interactions.
Oh, so they had tested it just elsewhere.
Yeah. The energy levels of atoms and nuclei respected it flawlessly. And because the model works so perfectly in those domains, the physics community treated it as universally applicable.
They just assumed.
Yeah, it was an extrapolation that basically became an unquestioned dogma. They assumed it applied everywhere, including the weak interaction, which is the force responsible for radioactive beta decay.
Right.
But it simply lacked an adequate dedicated test in that specific regime.
Which brings us to the interpretive crisis that basically forced the issue, which is the theta-tau puzzle.
Yes, the theta-tau puzzle.
So looking at the literature from the early 1950s, particle accelerators were producing these new exotic particles called K-mesons, or kaons.
Right.
And physicists isolated what they thought were two distinct particles, and they named them theta and tau. But looking at the data, I'm struck by this glaring contradiction.
It's a big one.
Yeah. These two particles had the exact same mass and the exact same lifetime.
Yeah.
And under the absolute rules of quantum mechanics, if two particles share all of those intrinsic properties, they must be the same particle.
They should absolutely be the same particle. Yet, the experimental observations presented an impossible conflict.
What was the conflict?
Well, the theta particle was observed decaying into 2 pions. The tau particle decayed into 3 pions.
Okay.
Now, pions have an intrinsic parity assignment that is negative. So a 2-pion final state yields an even parity assignment, because -1 squared is +1.
Oh, it checks out, yeah.
But a 3-pion state yields an odd parity assignment.
And since parity was assumed to be conserved in all interactions, the parent particle must have the same parity as its decay products.
Exactly. Meaning theta had even parity and tau had odd parity.
Wow. So the physics community was completely trapped.
Oh yeah, totally trapped.
Either theta and tau are two different particles that coincidentally have the exact same mass and lifetime, which is statistically just absurd.
Yeah.
Or they are the same particle, and parity is fundamentally broken in the weak decay process.
It was a profound theoretical deadlock.
Yeah.
And this is exactly where Sungdel Lee and Chen Ning intervened.
Yeah.
In 1956, they didn't just guess at a solution. They conducted a brilliant, completely systematic, interpretive review of the existing physics literature. They essentially audited the evidence.
So they went looking for the structural integrity of the assumption itself.
Yes. And they found that while there was exhaustive evidence for parity conservation in the strong and electromagnetic forces, the evidence for parity conservation in the weak force was strictly zero.
Wait, zero?
Zero. It wasn't that the weak force was proven to conserve parity. It was that no one had ever actually designed an experiment sensitive enough to test it.
Oh, wow. So they were just coasting on an assumption.
Exactly. Li and Yang realized the physics community was relying on this totally untested hypothesis. So they proposed several direct, decisive experiments involving weak decays to finally measure whether parity was conserved.
But proposing a theoretical test and successfully executing it are two vastly different things.
Oh, completely.
Here's where it gets really interesting. Because to observe this correlation between spin and momentum, you need an incredibly controlled system.
Right.
Like, you have to align the atomic nuclei of a radioactive isotope and carefully measure the trajectory of its decay products without disturbing the alignment.
Yeah, you need a master of experimental physics. And that was Chen Ning.
Okay.
She was already an established authority on beta decay.
Hmm.
Wu, collaborating with scientists Ernest Ambler, Raymond Hayward, Dale Hopps, and Ralph Hudson at the National Bureau of Standards, engineered this incredibly sophisticated laboratory setup to execute Li and Yang's proposed test.
I want to dig into the physical reality of this experiment because the setup itself is just a master class in thermodynamics and nuclear physics.
It really is.
They chose cobalt-60, right? Which is a highly radioactive isotope that decays via the weak interaction.
Correct.
But to align the nuclei, you can't just apply a magnetic field at room temperature because thermal agitation, the random jiggling of atoms, would just instantly destroy the alignment.
Precisely. The thermal energy would overpower the magnetic alignment.
Mm-hmm.
So Wu and her collaborators utilized extreme cryogenic cooling,
Oh, okay.
specifically a technique called adiabatic demagnetization.
Wow.
Yeah, they brought the cobalt-60 down to just a few thousandths of a degree above absolute zero.
That is unimaginably cold.
Yeah, and at that ultra-cold temperature, the thermal agitation was minimized. They then applied a strong magnetic field to polarize the cobalt-60 nuclei.
Which effectively lined up all their spins along a single axis.
Exactly.
So returning to our theoretical wedge, the stage is set. We have an axial vector, which is the aligned nuclear spin.
Yep.
And we're waiting to observe the polar vector, the momentum of the emitted electrons from the beta decay.
Right.
So if parity is conserved, the expectation is that there should be equal mirror-related rates of electron emission.
Right. You should detect just as many electrons shooting out parallel to the nuclear spin as anti-parallel to it.
But what actually happened?
Well, the observed reality completely shattered the assumption. Wu's team carefully measured the electron emission direction inside that cryogenic environment, and they observed a massive asymmetry.
Really?
Yes, the electrons were preferentially emitted in the direction opposite to the nuclear spin.
Meaning the weak force actually possesses a preferred direction.
Yes.
It structurally distinguishes left from right. That just changes the foundation of particle physics.
It was an absolute paradigm shift.
Yeah.
And it is crucial, we carefully parse the credit here, to maintain strict historical accuracy.
Of course.
Li and Yang performed the comprehensive theoretical review. They identified the blind spot and proposed the specific tests.
Right.
For this foundational theoretical work, they received the 1957 Nobel Prize in Physics.
Right. Okay.
But Qin Wu, Ernest Ambler, Raymond Hayward, Dale Hopps, and Ralph Hudson supplied the decisive laboratory evidence.
Yeah, the actual experiment.
Exactly. And it is a historical fact that Wu was not included in that Nobel Prize, despite her cryogenic alignment and experimental execution being the massive hurdle that proved the theory.
It just perfectly illustrates why science requires both the theoretical vision to ask the right question and the rigorous experimental innovation to actually answer it.
Absolutely.
So let's explore the fallout. The mirror is broken. Theoretical physics basically has to be restructured to accommodate a completely left-handed weak force.
Yeah. So to rebuild the model, physicists formalized specific terminology to describe this handedness in particles, primarily helicity and chirality.
So what does this all mean for our understanding of particles? Let's start with helicity.
Sure. Helicity is a measurable, pretty intuitive concept. It simply compares the direction of a particle's spin vector to its momentum vector.
Okay, if I can use a macroscopic analogy here.
Go for it.
It's kind of like a quarterback throwing a spiral with an American football.
Oh, right.
The ball has a momentum vector, it's traveling down the field, and it has a spin. So if it spins clockwise along its direction of motion, like a standard right-handed screw driving into wood, it has right-handed helicity.
Yep.
But if it spins counterclockwise, it has left-handed helicity.
That is an excellent visualization for helicity. Now, from the observed asymmetry in the cobalt-60 experiment, theorists developed a model-dependent framework to describe charged weak interactions.
Okay.
This became known as the V-A structure, which stands for vector minus axial vector.
V minus A, got it.
Right. When you mathematically subtract the axial vector current from the vector current in the equations governing the weak force, the resulting structure heavily selects left chiral fermions and right chiral antifermions.
And this is where we really have to clarify chirality, because it is deeply related to helicity, but they are not the same thing. I often see them conflated.
Like, very different.
If helicity is the apparent spiral of the football, what is chirality, like, mechanically?
Well, chirality is a more fundamental intrinsic property of the particle. It's dictated by how it transforms under the Lorentz group of space-time transformations.
Okay, that sounds pretty abstract.
To use another analogy, chirality is like a physical left-handed glove.
Yeah.
Regardless of how fast you run past a left-handed glove, it remains a left-handed glove.
Right.
Helicity, however, is frame-dependent for massive particles.
Right, because if I'm observing a massive particle with right-handed helicity and I accelerate my reference frame so that I'm actually traveling faster than that particle,
Yep.
from my perspective, its momentum flips direction. It appears to be moving backward relative to me
Exactly.
because the momentum flipped, but the spin didn't. Its helicity just flipped to left-handed.
You've got it perfectly.
Right.
You could overtake a massive particle, changing its observed helicity, but you cannot change its intrinsic chirality.
Wow, okay.
However, for massless particles, which travel at the speed of light, you cannot overtake them.
Because nothing goes faster than light.
Right. Therefore, for massless particles, helicity and chirality are perfectly identical.
Which perfectly brings us to neutrinos, because
Yeah.
at the time of this discovery, neutrinos were modeled as completely massless.
They were, yeah.
They are kind of the ultimate poster children for parity violation, aren't they?
They really are. The V-A structure dictates that the weak force only couples to left chiral particles.
Okay.
Because neutrinos only interact via the weak force and gravity in the minimal standard model. All observed interacting neutrinos are exclusively left-handed.
Wait, all of them?
All of them. And all interacting antineutrinos are right-handed. The weak interaction simply does not acknowledge a right-handed neutrino.
That is wild.
Yeah, to the weak force, a right-handed neutrino effectively does not exist.
It is genuinely mind-bending to realize there is a fundamental force that just ignores half of physical geometry.
Yeah.
But this raises a secondary theoretical crisis. If spatial reflection, parity, or P is completely broken by the weak force, what happens to the whole concept of universal balance? Like, did physicists simply accept an asymmetrical universe, or did they look for a new mirror?
Well, they sought a new mirror by combining discrete symmetries.
Okay.
So if P stands for parity, we must introduce C, which stands for charge conjugation.
And what does C do?
Charge conjugation is a mathematical transformation that replaces all particles in a system with their corresponding antiparticles.
So we swap every electron in an experiment for a positron.
Right.
Every proton for an antiproton, and so on.
Correct. Now, physicists knew the weak interaction violated P. It was also shown to violate C.
Okay.
But theorists proposed a combined symmetry,
CP.
combining them, right?
Yeah.
Yeah.
What if we apply spatial inversion A and D swap matter for antimatter simultaneously? For a brief period, CP symmetry appeared to be the perfect unbroken mirror of nature.
Oh, I see where this is going.
Yeah. The model suggested that an experiment conducted with left-handed matter would behave exactly identically to its mirror image constructed of right-handed antimatter.
But, you know, the history of particle physics is rarely that neat. I'm assuming this new mirror cracked as well.
It did. In 1964, CP violation was discovered in the specific decays of neutral kaons.
Oh. So nature's combined mirror was indeed broken, though on a much more subtle level. But it is vital to state clearly that CP violation is a distinct phenomenon.
Okay.
It's driven by different mechanisms in the standard model, and is not the same as parity violation alone.
So P is broken, C is broken, and CP is broken. Is there any discrete symmetry left standing?
Yes, CPT symmetry,
CPT.
which combines charge conjugation, parity, and time reversal.
Okay, throw time in there.
Yeah, if you swap matter for antimatter, reflect the coordinates in a mirror, and run the clock backward,
Yeah.
the laws of physics appear completely invariant.
Wow.
As of today, CPT is fundamentally baked into quantum field theory and is believed to be an absolute, unbroken symmetry of nature.
Fascinating.
Yeah.
Okay, I want to dedicate the next phase of our discussion to protecting the listener's understanding.
Good idea.
Because parity violation is so deeply counterintuitive, the popular understanding of it is just rife with misconceptions. So let's put this model to the test with some specific curveball.
I'm ready. Let's do it.
I'll present a speculative claim, and I want you to apply the theoretical rigor to it.
Sure.
First claim. Because parity is violated by nature, ordinary mirrors do not actually reflect reality perfectly.
That is completely false. Ordinary mirrors do not violate parity.
Good to know.
Yeah, the reflection you observe in a mirror is governed entirely by electromagnetism. Specifically, the interaction of photons with the atoms in the glass and silver.
And we know that conserves parity.
Exactly. Electromagnetism perfectly conserves parity. Therefore, parity violation is entirely invisible in our macroscopic everyday lives.
Excellent. Okay, next claim. Every fundamental force in the universe secretly distinguishes left from right. We just haven't built sensitive enough instruments to observe it yet.
That is entirely speculative and contradicts all current observation. This asymmetry is specifically isolated to the weak interaction.
Just the weak force.
Right. Gravity, electromagnetism, and the strong nuclear force have never been observed to violate parity. In all precision tests to date, those forces are perfectly blind to handedness.
Got it. Here is one regarding fundamental conservation laws. If parity, which is a fundamental symmetry, is broken, doesn't that imply that energy conservation might be broken as well?
A very important distinction to make there. Parity violation absolutely does not break energy conservation.
Why not?
Well, symmetries in physics come in two types, discrete and continuous.
Okay.
Parity is a discrete symmetry. You flip the coordinates, it's a binary change. The conservation of energy, however, is derived from a continuous symmetry.
Right. Time.
Yes, according to Noether's theorem, energy conservation arises mathematically from the fact that the laws of physics do not change continuously over time. So one discrete symmetry can be violated by a specific force, while fundamental conservation laws, like energy, linear momentum, and electric charge, remain perfectly valid.
That makes perfect sense. How about a historical misconception? I've heard the argument that Chen Ning simply followed Li and Yang's theoretical instructions, meaning she just confirmed a complete prediction without contributing any real experimental innovation.
That narrative fundamentally misunderstands the reality of experimental physics.
Right.
Wu did not simply confirm a prediction. Li and Yang proposed the measurement, but the technology to execute it did not exist off the shelf.
Yeah, you mentioned the cryogenics earlier.
Exactly. Aligning cobalt-60 nuclei required mastering extreme cryogenic technology, specifically adiabatic demagnetization, and successfully integrating particle detectors inside that hyper-cold, incredibly complex radioactive environment.
Which is no small feat.
No, her experimental innovation was the absolute prerequisite that made the observation possible.
That structural engineering alone is staggering. Okay, theoretical physics claim. The Higgs boson is responsible for giving particles mass, and because mass affects helicity, the Higgs mechanism is what actually causes parity violation.
That is false.
Oh, really?
Yeah. The Higgs mechanism provides the mathematical framework for particles to acquire mass. And it is true that the Higgs field interacts with left and right chiral particles to facilitate that mass.
Yeah.
However, the Higgs mechanism does not cause parity violation. The parity violation is fundamentally intrinsic. It is baked directly into the chiral structure of the weak gauge couplings themselves, completely independent of the mass generation process.
Okay, great clarification. Let's do one final clarification regarding Chen Ning Yang's broader legacy.
Sure.
Yang also famously worked on Yang-Mills gauge theory, so that must be the basis for his parity Nobel Prize.
No, you must keep those two contributions completely separate.
Oh, they're different.
Yes. Yang-Mills gauge theory is a monumental structural contribution to modern physics. It literally forms the mathematical backbone of the Standard Model.
Right.
But it is a separate piece of theoretical work. It was not the specific research cited by his 1957 Nobel Prize, which was entirely focused on the rigorous investigation of parity laws alongside Sundao Li.
Okay. Reviewing all of this, the discovery of parity violation feels like the ultimate masterclass in the scientific method.
It really is.
It proves that even the most deeply revered assumptions, these foundational premises that brilliant physicists accepted as absolute truth, they remain mere hypotheses until they are rigorously subjected to an evidential audit and physically tested.
That is the definitive takeaway. And, this narrative is not just historical trivia. The breaking of parity laid the vital groundwork for electroweak theory, which ultimately unified the electromagnetic and weak forces into a single theoretical framework.
Right, which is huge for modern physics.
Yes. Today, modern precision tests rely on this exact asymmetry. Experiments involving parity-violating electron scattering or atomic parity violation, they continually probe the parameters of the Standard Model.
Oh, wow.
We actively use this broken mirror as a highly sensitive tool to search for new physics, hunting for hypothetical right-handed weak currents or subtle deviations that might reveal entirely undiscovered particles.
It's as if physicists found a microscopic crack in the foundation of reality, and instead of patching it, they're using that exact crack to shine a light underneath the entire structure of the universe.
Precisely. A discrete mathematical transformation became an observable physical reality, and it fundamentally rewrote how we organize our understanding of nature.
Before we conclude, we have a mandatory closing block to share. This deep dive has been an independent Cosmora HQ overview of Chen Ning Yang's The Law of Parity Conservation and Other Symmetry Laws of Physics.
We highly encourage you to lawfully access the original Nobel lecture and the associated research papers to explore these concepts further on your own. We invite your thoughtful engagement with the material.
The history of science is fundamentally built on questioning the unquestionable.
It truly is.
So, leaving you with something to chew on, which symmetry that seems universal today might fail in an experiment we have not yet performed?